Yeah, let's take a few more minutes to give some people the chance to join the live. Um, Along in the meantime, feel free to share the link to the live. Um, yeah,
Already
we'll take a
done.
few more minutes and then
I
we'll
just
start.
want to 1 second. I want to share with everyone. Amin, can you not Amin Lev? Can you stop sharing the screen for a sec?
Well, I can't because right now it's not me sharing the screen.
That's me sharing.
Thank you.
I,
Thank you.
I stopped sharing.
Second. Yeah. Thank you. We want to share the new website for Web3 developers, which was only which is live now at web3devs.org. 1 second, we're gonna load the website. The new website connects with join a community and explore all three and crypto sphere, all the companies. And if you want to join as one of the speakers, DM us or contact us in any sort of way. Of course, you have the entire schedule for the events right here. If you want to sponsors, events, and of course our team, as you know, all be here. And the thing we are most excited to share here is our new careers page. So search for a Web3 expert. This is your place. For employers, you can, of course, post jobs and contact us to post jobs and recruit developers. And we have a few already very high level roles currently searching in Starkware. A very interesting site that will keep you updated on every new role that's going to be uploaded. Just join our Telegram. You can join right here. And this is the new website. We're very proud of it and very happy that it's now live. From that, I give it back to you, Lev and Amin.
Okay. Well, thank you for having me and giving me this opportunity to share about our project.
Awesome.
So,
I mean, do you want to wait 5 more minutes before we start to let a few more people to join the live? I think people are still joining.
sure.
Yeah, so we'll take 5 more minutes. We'll start at 5:10 and 5:10.
I'm trying to find your Twitter.
In the meantime,
Oh, there it is.
maybe I'll take this chance to present the community. Um, So yeah, for those who don't know, so I'll start with hello everyone and welcome to the seventh event in our special online meetup series, hosted by the Web3 Developers community. So before we will dive in, let me briefly introduce the community. So as you might know, we're a community of Web3 developers and builders founded on the open source values. And we were founded by Shaoli Redjwan and Roy Yasherov. And since our inception 3 years ago, we've consistently hosted in-person events, bringing together some of the brightest technical minds in space. Thank you, Amin, for emphasizing that. As many of you may know, we've recently expanded to online meetups, and we're committed to delivering top-tier technical content to the global Web3 community. Thrilled to have you with us today. So, to stay in the loop for future events and to continue building on what Alon already said, please make sure to follow us on all platforms. We're on X, Luma, Meetup, YouTube, Telegram, and more. You can see all of that on our website or Linktree. And a special thanks to our sponsor, Master KVC, and early stage venture capital specializing in infrastructure and deep tech across the Web3 ecosystem with a team of 16 world-class cryptographers and several technical experts led by our managing partner, Shaul Redjwan. MasterKey operates across all global crypto hubs, And now, well, let's say without further ado, I'm honored to pass the mic to Ameen Soleimani, the CTO of Expo. And thank you, Ameen. Now the stage is yours. Maybe you
Okay,
can start introducing yourself a little bit, and then we can dive into everything else.
cool, great, thank you so much. Should I proceed or should I wait another couple minutes?
Yeah, you can start. Let's say maybe say a few words about yourself, so our listeners may get a chance to know you a little bit before we start.
Fantastic. I love talking about myself. Um, Hi, I'm Ameen Soleimani. I'm a smart contract engineer, I guess. I've been building Solidity smart contracts on Ethereum and through various projects for almost a decade. I wasn't there at the beginning, but I joined sometime in 2016. And I worked at Consensus for Joe Lubin on like some micropayments, payment channels research, and then I went and started SpankChain. We built a payments product for crypto payments for the adult industry, and then I went and started MolochDAO, which was the third DAO ever, and it was basically an open source or it's a like punk rock themed uh, DAO to save Ethereum. This was in like 2019, and we raised a bunch of money from a whole bunch of individual Ethereum OGs, along with Vitalik and the EF and Joe Lubin and Consensus, and funded a bunch of cool projects, including Tornado Cash. And then later, once Roman Storm was arrested and Alexei was arrested for Tornado Cash, the MolochDAO turned into a legal defense fundraiser for them and helped support that. We were actually just outside of the courtroom. You can see this is Roman Storm. Privacy is not a crime. It's blocked by the table. Yeah. So we had some signs and we were posted up outside of the courtroom in the U.S. Today is the final day of Roman Storm's court case. He's on trial for money laundering and conspiracy to violate international sanctions, which each take a 20-year charge. So we're hoping for the best outcome for him. After that, I went and after MolochDAO, I started Rye and a spin out of it, which is High, and both of those are forks of Dai, which was the original stablecoin on Ethereum. Rye was like a automated, kind of like a central bank in a box. It like balances its own price in order to keep itself stable. And so it's as if the Fed wakes up every day and spits out an interest rate, except you fire everybody at the Fed and you replace them with a computer, and it just does the job for it. So it was pretty cool. And then, Rye is the one that's like ETH based on Ethereum, backed only by on the blockchain. And when we have that Merkle root, then the withdraw function has to prove that the deposit that is withdrawing comes from that comes from a deposit that's still currently on the association set. There's a scope, and the scope essentially just defines the pool, and so it's like basically a hash of the address of the pool and the chain that we're on. Each asset has a config, and so this tells us, how much. I think this is in state, right? These asset configs. Is here? No. This just tells us like how much the fees are and things like that. What the minimums are, certain things. So association set data is the association set. It's an array, and we just essentially push to it. And you have to prove that your deposit comes from is on the latest association set when you withdraw. And pre-commitments. This is a way of preventing users from depositing with any secrets that have already been used. in order to keep their money safe. If you have already used a commitment, you previously could have withdrawn, like deposited one that was already used, and that means only one of those would be able to be withdrawn ever, and that is not very good, because then the money would get stuck in the contract. So this was the upgrade we made, was adding this to this contract. So when you initialize this, there's this initialize function, and you set the owner and postman addresses and grant the roles. So the owner has the admin role, the owner has the owner role, and the owner also has the ASP role, and the or the ability to set the ASP role. And then you grant the actual roles, and the owner is the owner that is passed into this, and the postman is the postman address that is passed into this. I think when we started, we just used the same EOA, and then afterwards, from that EOA, we assigned to the postman the hot wallet. So the thing about the postman is that it's essentially a hot wallet, because it needs to be running on a server, and so we don't want it to have any permissions other than publishing the Merkle tree, so that it can't damage the system. And then the owner is an actual multi-sig that we can use that has more security, and it can be used to swap out the postman if there's any trouble. The worst thing that the postman could do is essentially approve of addresses that we don't want, or kick everybody out of the association set, but we would find out very quickly, and then we would be able to swap it out. So there's only one method that's an association set method, and that is called update root. And it takes a root and a IPFS string. And this is because we also publish the trees to IPFS so that people can download them separately without us. If, for example, our server goes down, and this is only allowed by the ASP postman, and all it does is what is this doing? Checking that this is a proper IPFS string, and then pushing it to this association sets array. And so it pushes this association set data, which has the root and the IPFS and the timestamp that we pushed it. And then it updates the index and emits an event that the root has been updated. And so if we wanted to nuke the root, we would just drop in a root here that corresponded to an empty tree, and then no one would be able to withdraw privately. And so this gives us the time to evaluate the deposits and make sure they're legitimate before we accept them. We're not in a rush. There's no fixed timer. It happens whenever we decide. So now there's a deposit function, and so this is what the user calls when they want to send money. And first thing that happens is they generate a pre-commitment, which is part of the commitment. In zero knowledge proofs and things like this, in Tornado, these things are called commitments, and it essentially is generated from a secret, which is a user generated secret, and a nullifier, and the nullifier can only be used once, but in order to not reveal it, it's hashed together with a secret, and that way the user can keep it private until they're ready to generate a proof from it. And so we call this, so this is essentially calling into handle deposit. And so there's two different deposit functions. This is the ERC20 implementation. That's why it has an asset thing and a value. Whereas this other one just has the pre-commitment. It doesn't have an asset because the asset is assumed to be the native asset. And then it just has message.value because it's payable. And so it works with the native asset instead of dealing with an ERC20. The ERC20 version has to do the safe transfer from, which pulls your ERC20 coins. And so you have to approve them beforehand, as we know in terms of how ERC20s work. So this handle deposit, we're going to go to that handle deposit. And so this does the bulk of the logic here. And so here we have, it's basically reading the config. So let me see if asset config, yeah. So this is the way that asset config is set. This is actually the end of the contract, but I'm skipping here just so you can see what's in it. This has a minimum deposit amount. The reason that's important is because, when we charge fees, we don't want to have to look up, how much, like vet, certain deposits if they're too small, because then it's not even worth the cost of us vetting it. And there's also a max relay fee bips, and this prevents the relayer from running away with all your money. And they say they're going to charge 100% of the fees, and then they actually don't. You don't get any money. If you're not paying attention, then you can lose it all. So we have those settings, and so this checks that. All right, let me scroll back up. To handle deposit. So here, this grabs the config for the pool by the asset. So each asset has its own config, and if no pool exists, then we revert. If the pre-commitment that is being used to deposit is already used, we revert. If the value is less than the minimum deposit value, we revert. We calculate some fees. This deducts the vetting fees. So it takes from the config, the vetting fees for that asset. Right now we charge about 0.5% on Ethereum, which is pretty standard for other privacy projects as well, and calculates the amount. And then it has this native asset value, and so this computes. This is just based on whether or not it's a native asset or not, and then it does the commitment, generates a commitment by actually depositing into the pool. So this is calling into the privacy pool's deposit function, and so this is a pass-through call, and so this goes into deposit here, and so then it does a couple steps here, and so it when it calls into the privacy pool's deposit, it has the address of the depositor, and so in this case, this was the message.sender, so the original transactor, the value of that, and so this is the value after the fees, is how much you can spend later, and the pre-commitment hash, which is the pre-commitment that the user has passed in. And so it checks to make sure the pool is not dead. And so the pool is dead is that what I was saying about earlier, is that we have the ability to just nuke all future deposits. And so if we nuke future deposits, then this will catch that and it won't allow you to deposit here. If the value is too high, it will revert. And then it computes a label. The label is very important. I'm not going to get 100% into it now. I'm going to explain it at a higher level, and I'm going to let Lev talk more about it in the circuits part of this. The label is unique to a deposit. And so when you deposit, so it has a scope, which is based on this contract. So the scope is a constant. Where is the scope? Yeah. So scope is defined. Okay, this calls into the state, so it's probably set in here. Scope, right? Yeah. So this is a immutable, just a variable that's set in the constructor of the privacy pools contract, and it's the hash of the blockchain ID and the specific asset. And so this label, it's also based on the nonce, and this nonce gets incremented. And so this is based on the number of deposit you have. So it starts at 0 and then goes up. And so it's unique to this specific deposit. And so this is what allows us to make sure that, if I withdraw and I redeposit, I deposit 13, I withdraw 5, there's 8 left in the pool. that gets redeposited, the way the redeposit works is that the redeposit has the same label, and this is enforced by the zero knowledge proof, as the original deposit. And so that way, if I kick out the original deposit, then I won't be able to prove that the that the money that is left in the pool can be withdrawn, because I can't prove that the original deposit is still on the association set. And so this is nice. If we didn't have this label thing, basically the way this would work is that if we let money into the pool ever, it would stay there forever, and there's nothing we could do to kick it out. And I think it's much more scalable to be able to.
There is no sound from
You, yeah. Ameen?
I mean, you muted yourself.
I don't
Yeah.
know if I muted
Now
myself.
you're back online, yeah.
How long did I mute myself for?
No. 5
For a
seconds.
few seconds, and also presentation is you need to
disconnected.
show it once again.
Thank you. Feel free to continue to yell at me if I do anything silly.
No problem. I'm here. Just put the camera off.
All right. So anyway, we save the label. It's unique to the deposit. It lets us kick people out. And so then we compute the commitment from the value, the label, and the pre-commitment hash, and then we insert it. This is an insert that is this insert function. It's not implemented on this one. This is in the lean IMT tree, I think. Okay, where did I go? Yeah. So insert here. Yeah. Okay. So insert is implemented here, and so this is inserting a leaf into the state. And so the leaf, it's this is a Merkle tree, so it's creating a Merkle tree, and so it's adding a leaf. Make sure you're not too deep. It updates the next index. It keeps track of a couple of these, like I think it's max root history is like 32. That just means you can have like, if you deposit and there's like 32 other withdrawals in the block, you can still withdraw. And so it's not a problem. And so then it updates the root and emits an event that you inserted this leaf into the tree. And then it pulls your money. And so let's see where pull is implemented. Yeah, so pull. Okay, so I think that'll also be in state. Pull. No, okay. It's asset override. So this is right. These are these functions. So in privacy pools, this is very basic. So this privacy pool simple is for ETH, the native asset, and so pull is just checks that the message.value has the money. If you do a complex, this is the ERC20 version, and so this checks that you actually do the ERC20 transfer, and so that you actually go get the money. So close those, and so that's implemented there. So that is the deposit function that uses both the entry point and the privacy pool. Okay, so now let me go to the next function, which will be relay. And so now we're going to talk about how you pull money out. So I'm going to do this in reverse, actually. So I'm going to come here. So I'm going to note that when you do this relay, you call pool.withdraw. And so I'm actually going to go look at pool.withdraw first, and then come back and do the relay. So let's go here and look at the privacy pool withdrawal function. And so in this withdrawal function, this is what allows you to withdraw privately. And so in order to withdraw privately, we have to verify certain proofs. And the proof that we're verifying is it's based on the withdrawal circuit. And so this is the one that says, I actually, have not only not spent the money, but my deposit is still in the association set. And only if that proof is valid, I'm allowed to spend the money. And so this spend takes the nullifier hash that I'm spending. Every deposit, creates a commitment, and then the commitment is nullified. And so when this is nullified, I can no longer spend that commitment. And it also introduces a new commitment because this is how the partial withdrawal system works. So it does the same insert that we saw before up here. Insert a commitment, we insert a new commitment. And so you kind of have to do this every time, right? Because let's say I withdrew like 10 and like I deposited 13 and I withdrew 5. I'm redepositing 8, but if I deposited 13, I withdrew 13, and I skipped this line, it would be obvious that I have withdrawn all of the money. And so you always create a new commitment, even though sometimes it is 0. And that way the people observing can't know that I have actually withdrawn my whole balance or just some of my balance. And then what happens is we transfer funds out to the processor who processes this withdrawal. And so this processor is, in this case, the entry point itself. And then this transfers the money to the relayer and the destination address. And so this, when I call withdrawal here, I'm as part of this, I'm actually providing this the address of this entry point contract as my processor field, and then it pulls out the withdrawn value to that. And so now that I've done this, I'm going to go back to the relayer and show this part. And so the one thing to note here, actually, with the privacy pool is that this withdrawal verifier, let's see if I can find it. Yeah, is this the one with the valid withdrawal? Yeah, so one thing I skipped here is that there's this modifier here, right, that has the valid withdrawal. And so this is making sure that all of the withdrawal parameters are correct, and that the proof is correct. And so this checks certain data on the proof. For example, it has a reference to the entry point. And this is why it's important for the entry point to be a upgradable proxy, because we want this contract, the privacy pool contract, to be immutable, which means that we don't want to have to update the privacy pool contract if we update the entry point. And so we can make sure that the entry point has the same address, and that way the reference is not broken. And so that way we can always figure out the latest route that is published to the entry point. And this is the latest route of the association set that is published by in our case, Oxbow, the ASP postman. And so it makes sure that the route that you are proving against, that your deposit is part of, is in fact the latest route in the entry point. And it checks some other stuff as well. the sender of this has to be the processor, so this prevents man-in-the-middle attacks. So you generate a withdrawal, you select where the money is supposed to go, and then only that person is actually allowed to call this contract, and person or address. And make sure that the context is matched, so that you got the actual hash of this specific pool, and and then make sure that your state tree is correct, and so forth. So now let me go back to the relay function. So I'm going to go through this. When you relay, so as you guys saw, I have certain parameters of the withdrawal, and I have the proof that I've generated along with it. And so, if the proof value is 0, I revert. If the processor is not this, then I revert. So, this relay enforces that it is in fact the processor of the withdrawal. It fetches the pool by its scope. It stores the pool asset to make it easier to look up later. It checks this is a balance before, and so this is checked down here to make sure that this doesn't end up with any money or lose any money, I should say. So then what happens is it calls the pool withdraw function, which we just saw. It has some relay data, and the relay data tells us, how much fees the relayer wants to charge, and this is flexible on purpose so that the relayer can essentially scale their fees up and down with gas, as we saw. And so, if gas prices are high and I want to withdraw, well, the relayer needs to be able to say, I'm going to charge a little bit more bips on this withdrawal in order to make it work. And that is enforced up to this max relay fee bips. This should probably be a less than or equal to, because max implies that you can be at the max, but oh well. Then it saves the withdrawal amount from the proof of how much you're trying to withdraw. It does a fee deduction, so it calculates how much is the amount that's going to the user from the withdrawal amount. It calculates the fee amount, and then it transfers the assets, because in this pool withdraw, this contract is going to end up with the money from the pool. So as an intermediate step, it's going to go to the pool, it's going to withdraw the money here, and then it's going to transfer it out. And so it's going to transfer the amount after fees to the recipient, and it's going to transfer the fee amount to the fee recipient, which is the actual relayer who is submitting this transaction to the blockchain. And so that is how relaying works. I'll go through the rest of the ASP quick, and then the rage quit functions, and then I will kindly take off. So registering the pool. This is basically how we just make sure that we want to add a new ERC20 token. So we have to register an asset, and we have to provide the parameters for the config. So we have to say how much is the minimum deposit, how much is the vetting fee that Oxbow takes, and what's the max relay fee to protect our users. We've been setting this to about 5% so far. If gas is very high and your deposit is small, you might not be able to withdraw, because it might cost literally just more than the fee bips to allow you to, but otherwise it works in most of the cases. So when we register a pool, it stores the asset config, makes sure the pool isn't dead. It makes sure the pool is not already registered. So we don't have two pools for the same asset. It computes the scope of the pool. This is, it's already the way this works is that you actually deploy the privacy pool contract first, and then it's immutable, and then you register it with this contract with the entry point. And so you come in here and you call this function. So I'll go through this constructor, right? And so you have the reference to the entry point, the reference to the withdrawal verifier. And so this is where the verifier for the withdrawal circuit lives. This is where the verifier for the rage quit circuit lives. And these are different because when you rage quit, you're proving a different thing than when you withdraw. When you're rage quitting, you're just proving that I have money still in the pool, and I'm, I can withdraw it. When you're withdrawing, you're proving that not only do I have money in the pool, but also my initial deposit is still, on the association set. And then you give it the asset that you want to create this pool for, and then it also initiates the state. And so this comes here, calls this constructor, initializes all of these, hard-coded, or not, well, hard-coded, but immutable parameters for the entry point, withdrawal verifier, and rage quit verifier. So none of those can change, and that's what makes this immutable. And then we initialize the scopes and the configs, and we set the pool config based on the config that was passed in for all this information. And this is just to help deal with the ERC20. This approves, Infinity approves the privacy pools contract from the entry point. And then we emit pool registered. We also have the remove pool function. And so this just does all of that in reverse, and it allows us to delete the pool. And we can delete a pool and then add it later if we want. And so this allows us to do that. We can also update the pool configuration. So like right now, it's free. The vetting fee is set to 0 for example, all of our stable coins that we've added for a limited time. But then later we're going to set this higher again and charge fees again. That was to create, an incentive for people to deposit. Wind down pool. And so this is just the, we can, for each pool, give it the kill function. And so this calls pool.winddown, wind down. And so only entry point can call this function. And so the entry point itself has certain permissions on the privacy pool. And, you can't call it twice, doesn't matter, but then it just sets dead to true. And if it's dead, comment die, right? Wonderland guys are pretty funny. So dead is set to true. And then from that point, it checks is dead, pool is dead. And so it won't allow you to deposit anymore because the pool is dead. Pool dead. Sad. So that's winding down the pool. Only the owner can call this. Note that all of these configuration functions are all only the owner, only owner role, right? The only thing that the ASP postman can do is update the root, and that's to have this nice separation of responsibilities, hierarchical permissions, and all that. So then we have withdraw fees. This allows us, our vetting fees just stay on this contract. And so if we want to withdraw them, we have to call this withdraw fees function. And that allows us to send the money to our multi-sig. These are view methods. So you can check the latest route. It just grabs the, has this index. It checks the length of the association sets, and it returns the last one, the last route. Or you can get a previous route by the index. And so you pass in an index and it gets the route at that index. These are some other functions. These aren't super interesting. These are just for making the upgradable proxy work, receiving assets, transferring assets, checking balances, deducting fees, setting the pool config. So that leaves us with my favorite function, the rage quit. And so the rage quit is, if you get kicked out of the association set, or maybe you never got approved in the first place, you've got sketchy money, from, I mean, this actually happened to us, right? So like somebody deposited from Novitex. Raise your hand if you know what Novitex is. Just kidding. I can't see any of your hands. It's the largest Iranian exchange. So those people are either my compatriots or my enemies. They didn't contact me. I don't know who their money is. Unfortunately, I can't take that kind of risk. So we did not allow it into the pool. And so if your money is, you did deposit, we don't accept you, you have to rage quit. And you pay us either way, by the way. We take the vetting fee either way. And this is important because if you're trying to spam us, if we didn't have a vetting fee that we took either way, you could basically just spam us forever and cause us grief. And so this makes it somewhat expensive to try and, sneak money into the pool because, you still pay us. So there's a, this is the rage quit. And so this has the different proof. And so remember, this proof is just that you have the money. And it also enforces that only the original depositor. So we stored the label, the depositor, we set this to message.sender up here. So this was the depositor. And so we have a reference to what the initial depositor of this label, of this was. And so that address is allowed to withdraw it. And that makes it so that they don't get any privacy. And then we verify the proof with the Groth16 rage quit verifier. And then we check that the commitment exists in the state. What is this? Isn't state function. So this is checking that the Merkle tree has the leaf. So it has been deposited, in the past. It's a valid deposit or commitment. And then it spends the nullifier hash, and so it marks the existing commitment as spent, and it transfers all of the funds to the rage quitter. And rage quits are all or nothing. You can't rage quit like half of your money. You have to rage quit all of it. And so then this sends all of the money to the message.sender because only the original depositor is allowed to call it, and then it emits the rage quit. And that is all for the rage quit. And so now I can stick around for a little bit, answer some questions. The rest of this I'll hand off to Lev. He can walk through these circuits. The commitment one is the easy one. And then the Merkle tree is the commitment one is actually the rage quit one. It's also called commitment here because it's just checking to see that you have a valid commitment. And then this is the withdrawal commitment, or withdrawal circuit, which not only enforces that you still have the money, but also manages the making sure that you're on the latest association set, and also manages the redepositing. So I'm not going to go through all this, but I'm going to give Lev the opportunity to stop sharing my screen for a second and answer questions if there are any.
There are any questions in the chat? We're streaming also on Twitter and LinkedIn and YouTube. I'll collect questions, and if there will be any, I'll shoot them right at you, Ameen. In the meantime, Lev, I think you can start, and we'll maybe pause or collect for the end, Ameen.
Sure.
There's a stipulation here. The stipulation is I'm leaving. Because
I think this is your time to share where people get a hold of you or contact you or follow you.
Yeah. Please follow me on Twitter at Ameen Sol, at Oxbow0expo IO. The website is oxbow.io, so 0expo.io. And then we also have at Privacy Pools. We have the nice corporate account for Oxbow, the verification company. It's a compliance company. And then we also have the meme account for Privacy Pools. where we can post like 300 memes because we have 300 ETH in the pool. We're happy about it. So thank you all for your time. The reason I have to go is I made this plan a month ago, but it is Roman's in court, and I want to catch the closing statements. This is Roman Storm. Privacy is not a crime. This is a T-shirt from our protest that we had right outside of the courthouse. We're about to see if the U.S. government allows us to have privacy in the future and doesn't put the devs in prison. I hope it works out.
I think we all cross our fingers.
Yeah.
And,
So thank you
see.
all so much for your time. Appreciate the opportunity to be here. Thank you so much, Lev, for covering the second half of this and letting me run away. So
I'd like to thank you a lot.
Bye-bye.
take care.
And Lev, I think it's your time to shine.
Yeah, okay, let's go. So let
So
me
bye-bye.
try to, yeah, I'll just quickly go through the circuits. So I'm not sure how familiar are you with like the, can you see my screen, by the way?
Yes, we can see.
Okay, great. So yeah, I just wanted to quickly go through the circuits. So I'm not sure how familiar are people with like the concepts of zero knowledge proofs. So basically, like the circuits get compiled, and they're written in circle language, and they get compiled into these certificates, so which are like called proofs. So basically, if you can like find the attesting like witness to the circuit, then you are able to make a proof. And it does not reveal any data about the internals of the internals of like the inputs that you put into this circuit, and so this can be used to achieve privacy. So I will go quickly through like what the circuits are and how are they used. So first of all, this commitment circuit, it is also used as rage quit. So it makes something called pre-commitment, and it makes it by hashing nullifier and secret with like popular hash function Poseidon, which is very efficient in circuits. So it hashes like your secret input nullifier and secret input secret, and it obtains this pre-commitment. So these two are pre-commitment. And then commitment, so it will be in this pre-commitment hasher out. And so the actual commitment is like made from pre-commitment, the value and the label. And the reason for this design is we want our initial contracts to like, so the way we create initial commitment is not by making a proof, by just the contract adds a leaf to the numerical tree. I mean, have shown that, by the way. So basically, the value is known. It's the value of your deposit in that case. And the label is defined deterministically from your deposit. And so, so if you're depositing the money, then you only send the pre-commitment, and the commitment will be computed by the contract. Okay. And so outputs are commitment and nullifier hash. And nullifier hash is predictably a hash of the nullifier. So when we will spend the commitment, we will show the nullifier, and it will be checked that nullifier is actually a preimage of the nullifier hash. Okay. So, and this circuit is also used for rage quitting. When we are rage quitting, we just basically show the pre-commitment. Or I think some different signals are labeled as public. I will talk about this later. So now let's go through withdrawal circuit because it's like the main interesting thing. So it gets a bunch of inputs. So what are these inputs? These inputs are public, and these are the value that we are withdrawing, the state root and state tree depth, which are like basically parameters of the Merkle tree. And these are parameters of ASP Merkle tree. And context is just some value which is used to not confuse the pools between each other. Okay, and so the private signals is like we do not show them, and they're used to actually show that you have a valid commitment in the tree. So, I mean, say that you are proving that you actually have money in the pool, but what you are proving is you control the valid leaf or commitment of the valid leaf in the tree. And then, additionally, the contract, I probably should also show the contract, but I will do it later. It also checks that your nullifier is not spent. So basically, you cannot spend the same leaf twice. So the circuit itself doesn't check that you still have money, but it will show the nullifier, and if this nullifier is already spent, then you will not be able to withdraw. And this is checked on the contract side. And these are some witnesses for the Merkle tree. I will go through them later. Yeah, okay. And so what does it output? It does output a new commitment which should be added to the Merkle tree by the contract, and it outputs the nullifier hash like of the existing commitment. So this is to actually nullify it. And this is to like add the remaining money back to the pool. So like if you are withdrawing partially, then this new commitment hash will be a leaf that is added to a Merkle tree. So what you could imagine is like you have a single UTXO, which like when you are withdrawing, like a new UTXO is created, like a leaf, the previous one gets nullified, and the new one is created with like the remaining money. Okay. So what it actually does? Well, we compute the existing commitment, which is just using the same, which is just using commitment hasher, just this circuit. And this is provided our data, like our label, some values. So we just compute some commitment. And we will attest, it will be attested a bit later, like in the third step. So we output its nullifier hash, and we attest that it actually exists in a state tree. I will go into the details of how Merkle tree works later, but like if you believe that Merkle tree works, okay, this just checks that the commitment is actually in the tree. So this is a component which checks that it's in the tree. And what's important, it also checks that the state root is the state root provided by the contract. Because otherwise you would just falsify and give me a different Merkle tree, but there is a public input which is a state root, and it checks that it's provided by the contract. So, okay. And we also verify that the label is in the ASP tree. So label is something that is preserved during the redeposit process. So basically, if you are withdrawing money, the important part about the label that it is getting preserved. It's basically a label of your account. So, or like IDs of a single deposit and all of its descendants. So, you will see that it gets preserved. And so, if you once again, if you believe that it is preserved, then basically, if your label is an ASP3, you are able to do the withdrawal. And this is this retroactive bond property. So you can, like, ASP provider can potentially just remove some label from the tree, and then they will only be able to rage quit, even if they already, like all the money that they did not remove from the pool, they will only be able to rage quit. So we check that the withdrawal is valid, which is just checking that remaining value. So remaining value is existing value minus withdrawn value. Remaining value is checked to be non-negative, from 0 to very large number, 2 to the power 128. And withdrawn value is also non-negative, and existing value is non-negative by assumption. So this is just the check that we do not get any overflows, like pretty standard stuff. Okay. I'm not sure what this does even. I think it's not needed, but I will figure it out later. Interesting. Anyway, we compute the new commitment, and this is like value is remaining value, label is preserved, and nullifier and secret are like new nullifier and new secret that we just provided. Here. So what's important is like on the level of the UI, nullifier and secret are derived from your seed phrase, but here they are completely unconstrained. So actually, you could use any pair of nullifier and secret. It theoretically allows you to burn your money if you do it twice, like and use the same nullifier. But you should never do this, and UI prevents you from doing this. Okay, so output new commitment hash. This is like the new leaf that will be added to the tree. And this is a magic talisman which does absolutely nothing, but people do this for fun. Like actually, there was some very old vulnerability which was countered by, like, if there was a public signal which is not constrained by any by anything, but you want to add it to the context, then like there was a vulnerability, actually vulnerability in Gross 16 protocol itself, which was countered by adding this constraint to the unconstrained signal. But right now it's not needed anymore because Circom compiler does it for you, but people do this from time to time just to have fun, I guess. So these are like the most I guess like important circuits, and then like Merkle tree is like the actual like heavyweight, which does this actually does the management of the Merkle tree. So this is what's called lean incremental Merkle tree. Basically, how it works is it can have some depth, and if its depth increases to yes, sorry, some question. Yeah, okay, this is just thanks, Ameen. Yeah, Ameen already left, but
yeah, it was just a notification that someone joined.
Oh, okay. So anyway, so Merkle tree. So this Merkle tree, it sort of can have different depth, and it's like it will double. So if the amount of leaves is 2 to the power k, then its depth will increase by 1. So when we have inclusion proof, we have like actual depth and we have max depth. And because we are in a circuit world, then proof always will like be about basically something of max depth, but it also needs to handle the actual depth of the tree. So let me show how it works. I will introduce the signals as we go. Yeah, okay, this just checks that actual depth is less than max depth. We have leaf index, which is the leaf index is translated to a numerical path. So it's like a sequence of commands which tell you if you go to the left node or to the left child or to the right child. So zeros are left child and one is right child. And so we transform it to bits, which is done by this component called num2bits. And this is actually quite funny because there was a recent bug found in a lot of implementations of Miracle 3, which provided, instead of this leaf index, they provided the path itself and were not checking the bits, that these bits are actually bits. But in this case, these are actually actual bits because they are produced by num2bits component. And so this implementation is not effective. And we start, so logic starts from the leaf and then goes upwards towards the root. So we initialize with leaf value, and then we take, basically we take the current, how to say it, so basically we have provided the list of siblings, right? The numerical witness. And so we either take nodes I and siblings I, and this is computing nodes I plus 1, by the way. What's happening? We're computing nodes I plus 1. So we are either hashing nodes I, siblings I, or siblings I, nodes I, depends on whether the left, whether nodes I is left child or right child. So if it's left sibling, then if it's 1, then it's left sibling, and if it's 0, it's right sibling. So this component just sort of chooses either this or this, and then we hash it, and we get, wait a second. No, we hashing both. Well, this is actually a very strange way we do this. Wait a second. Oh, okay. So I'm sorry. And actually, this is adding. So this is the hash, which would be the next element of the tree, and this is handling the depth which is less than maximal, because if sibling is empty, then we just keep the previous node, so it does nothing. And it outputs the computed root. So let me check what the sibling is empty. Sibling is empty. This is kind of component. Sibling is empty. That's interesting. So right now it's not checking the actual depth anywhere here. It's just checking that the sibling is that provides the sibling is 0. I will need to recheck this. But basically, what it should do, and I hope it does, is that for a tree which is less depth than maximal, you can provide lesser amount of siblings and set remaining to 0. Okay, so and it outputs the computed root. And remember that in withdrawal circuit, we checked that this root was actually the root the root which was provided by the contract. And I guess these are basically the overview of the circuits. So commitment can be also used as rage quit circuit. Because in rage quit you need to just you just basically show the commitment, and this template allows you to prove that you control it. And it gets nullified by the contract once again. So I guess this is like the rough overview of what the circuit part of the system does. Any questions?
And thank you so much, Lev. Currently, we don't have any questions. Thank you all for being here. Thank you, Lev, and of course, thanks, Ameen, for this amazing talk. You're all welcome to follow us on our social platforms, on LinkedIn, Twitter, Luma, and sign up for the calendar to see new events and the new careers page, which is highly relevant to everyone in the Web3 space. And that's it for today. And see you in the next one. Bye-bye.
See you. Bye-bye.